For light years away, our nearest stellar neighbor kept a profound secret. A silence that haunted astronomers for generations, while the galaxy whispered of thousands of alien worlds. For decades, our most powerful telescope strained against the void, searching Alpha Centauri, a star system practically in our cosmic backyard. Yet, it remained stubbornly blank. Thousands of exoplanets were discovered around distant suns, their light taking centuries to reach us. But the system next door, so prominent in our night sky, revealed nothing. A frustrating, almost poetic void. Then, the James Webb Space Telescope turned its golden eye. And in that brilliant, familiar glare, scientists detected something unexpected. A dim spark appeared beside the star, then vanished. What Webb uncovered forced us to rethink how we search for worlds beyond our own. Alpha Centauri isn't just one star, it's a family. Two primary stars, A and B, dance in an 80-year gravitational waltz. Similar to our Sun, they presented a paradox, close, yet impenetrable. Its binary nature, once thought to hinder stable planet formation, and its intense brightness, the third brightest star in our sky, made detection incredibly difficult. Imaging a faint world there was like seeing a snowflake against a searchlight. Despite these hurdles, Alpha Centauri remained humanity's imagined first step beyond our solar system, a logical first harbor. But what kind of harbor? A barren system, or one teeming with worlds? Webb wasn't built for blazing nearby stars. Its mirrors were polished to catch faint infrared whispers from the early universe. It was designed for the cold and the quiet. Alpha Centauri is neither, it's aggressively bright, threatening to overwhelm Webb's delicate detectors. Yet, scientists believed planets glow with heat. Even a cold world radiates faint infrared light, detectable by Webb's mid-infrared instrument, MIRI. This could reveal a mature, billion-year-old planet, unlike the hot, young exoplanets previously imaged. To overcome the blinding glare, Webb deployed its coronagraph, an artificial eclipse created by a tiny internal mask. This blocked the star's central light, reducing its brilliance by thousands of times, allowing faint objects to emerge. Alpha Centauri's rapid motion and parallax, its apparent shift due to Earth's orbit, demanded extreme precision. Webb had to perform a blind offset, aiming indirectly to place Alpha Centauri precisely behind the mask. The companion star, Alpha Centauri B, further complicated matters, scattering light that had to be meticulously modeled and subtracted. Months of simulations and refined procedures preceded the actual attempt. In August 2024, the refined observing campaign executed. Webb stared for hours. Data streamed back, raw images chaotic with diffraction spikes and scattered light. But astronomers used reference star differential imaging, meticulously subtracting known instrument behaviors layer by layer, peeling away noise like clearing fog from a window. And then, from beneath the suppressed glare, a faint signal emerged. Small, dim, a point of warmth positioned just beyond the most intense region of starlight suppression. Webb had done what many thought impossible. It had looked into the glare of our nearest sun-like star and found something that should not have been easily visible. The silence was broken. The processed images revealed a faint, point-like source, stable and distinct, about 1.5 arc-seconds from Alpha Centauri A. It glowed roughly 10,000 times dimmer than the star, a statistically significant signal. The team cautiously labeled it S1, Source 1. Its apparent separation corresponded to roughly 2 astronomical units from Alpha Centauri A, placing it near the outer boundary of the star's habitable zone. Based on its infrared brightness, S1's estimated temperature was around 200 to 250 Kelvin, about -50 degrees Celsius. This was consistent with a Saturn-mass gas giant. This made S1 historic, the closest, oldest, and coolest directly imaged candidate, much closer to its star than any previous discovery. But before any celebration, every alternative explanation had to be dismantled. Was it a background galaxy? No. A foreground asteroid? No. An instrument artifact? The signal behaved like a real planetary source. It passed every internal test. Still, caution ruled. A single observation is a beginning, not a conclusion. Planets move, following Kepler's laws. Orbital motion would be the ultimate proof. If S1 truly orbited Alpha Centauri A, it would shift position over time. If it appeared again at a new, predicted location, the case for a planet would dramatically strengthen. Follow-up observations were scheduled for early 2025. The expectation was straightforward: S1 should be there, perhaps slightly shifted, but detectable. If it reappeared, the mystery would transform into confirmation. If it didn't, something far stranger would unfold. Because planets orbit, they shine, they cool. But they do not simply vanish. February 2025 arrived with quiet anticipation. The follow-up observations weren't experimental this time. The procedure had been tested, the blind offset worked, the coronagraph held steady. If S1 was a planet, this would be its moment of proof. Webb once again aimed toward Alpha Centauri A. Hours of infrared light poured into its detectors. Scientists began processing immediately, converting photons that had traveled over 4 years. At first, everything looked familiar: diffraction rings, residual glare, the chaotic fingerprint of a bright star seen through a coronagraph. The team ran the same subtraction methods, reference star comparisons, and principal component analysis that had revealed S1 in August. They focused on the predicted region. Nothing. No faint, no whisper of warmth, no statistically significant signal. They widened the search, exploring a range of possible new positions simulated by orbital models. Still nothing. They reprocessed the data from scratch, adjusting parameters, using different noise thresholds, trying alternative subtraction strategies. Independent teams analyzed the images separately to avoid bias. The result did not change: S1 was gone. A particular silence followed this unexpected null result. Not failure, but confusion. The data were clean. The telescope had performed flawlessly. Sensitivity levels matched or exceeded those of the August observation. If a Saturn-mass planet was sitting where models predicted, Webb should have seen it. But the frame showed only empty space. April brought another chance. Perhaps February had caught the planet at an unfortunate orbital phase, too close to the star, partially buried in glare. A few more months might shift it outward again, restoring visibility. April's data arrived. The analysis repeated, and again, nothing. The object that had appeared with statistical strength in August 2024 didn't show itself in February or April 2025. For a moment, the simplest explanation loomed largest: maybe S1 had never been real. Even a statistically strong, 5 sigma detection doesn't guarantee truth. Rare fluctuations happen. Instruments produce artifacts passing multiple tests before revealing themselves as illusions. Astronomy has a history of celebrated signals later reclassified as noise. But something about this case resisted that conclusion. The August detection behaved consistently across independent data subsets. It did not flicker or smear, matching a point source's expected behavior under the instrument's optics. And yet, planets do not vanish. Or do they? To understand, astronomers turn not to the telescope, but geometry. A coronagraph doesn't see equally in all directions. Its sensitivity is shaped by physics. Light bends around the mask's edges, creating blind spots. Imagine shining a flashlight through a small opening. The beam isn't perfectly uniform, there are patterns, brighter arcs, dimmer patches. A tiny object drifting through that beam might appear bright in one position and invisible in another, even if it never changed. If S1 followed a highly eccentric orbit, its distance from Alpha Centauri A would vary significantly over time. At its farthest point, called a pastron, it would sit at maximum separation, easier to detect. As it moved toward periastron, it would draw closer to the star, entering regions where residual glare overwhelms faint planetary heat. In that case, disappearance meant concealment, not destruction. Orbital simulations began in earnest. Scientists generated thousands, then millions, of possible orbital paths. They varied eccentricity, inclination, orientation, and period. They asked a simple question: for how many plausible orbits would a planet be visible in August 2024, but hidden in February and April 2025? The answer was startling. More than half of stable orbital configurations produced exactly that pattern. In these scenarios, S1 would have been near a pastern during the August observation, far enough from the star to emerge from the glare. By early 2025, it would have moved inward along its elliptical path, crossing into a region where the coronagraph's contrast performance drops below the detection threshold. The planet would still be there, Webb simply couldn't see it. This possibility reframed the mystery entirely. The disappearance no longer contradicted the planet hypothesis. Statistically, non-detection in early 2025 was more likely than continued visibility for many orbital solutions. But the story grew even more intriguing. In 2019, years before Webb's observation, astronomers using the Very Large Telescope in Chile had reported a faint, tentative signal near Alpha Centauri A. That candidate, labeled C1, was never confirmed. Ground-based observations suffer from atmospheric turbulence that can mimic planetary signals. Still, C1's reported position fell closer to the star than S1's August location. What if they were the same object? If a single planet moved along an eccentric orbit, it could have appeared closer in 2019, farther out in 2024, and then hidden again in 2025. When simulations incorporated both the 2019 hint and the 2024 detection, the results became even more compelling. A family of orbital solutions satisfied both positions, naturally producing non-detections during the 2025 follow-ups. In this picture, S1 is not a ghost. It is a traveler moving along a stretched ellipse, periodically stepping into visibility before slipping back behind a curtain of starlight. The orbital parameters suggested something unusual, an eccentricity near 0.4, far more elongated than Earth's path. An orbital period between 2 and 3 Earth years, and an inclination tilted significantly. Such an orbit would make S1 unlike any major planet in our own solar system. It would also explain the vanishing act. At certain points, S1 would sit in the coronagraph's sweet spot. Months later, it would drift into regions dominated by diffraction and glare, becoming effectively invisible yet physically present. The February and April observations did not kill the planet hypothesis. They made it stranger. Because now, confirmation required patience. If the simulations were correct, S1 would swing outward again, returning to a favorable position in mid to late 2026. Another window would open, another chance to catch it in the act of orbiting its star. If Webb observes Alpha Centauri during that predicted window and finds S1 near the expected location, the case for a real planet becomes overwhelming. A consistent, gravitationally bound trajectory across multiple years would eliminate nearly all alternative explanations. If it fails to reappear, then the mystery deepens once more. Either way, the stakes are enormous. What began as a faint infrared point became a test of orbital mechanics, instrumentation limits, and human patience. The planet that wasn't there may be exactly where physics says it should. Hidden in plain sight, waiting for its orbit to bring it back into view. And somewhere 4 light-years away, Alpha Centauri continues its quiet dance, indifferent to the debate unfolding on a small blue world that has just begun to see clearly. Let's assume for a moment that S1 is real. Not a fluctuation, not an artifact, not a background illusion, but an actual planet orbiting Alpha Centauri A, our nearest sun-like stellar neighbor. What kind of world would that be? The infrared brightness measured by the James Webb Space Telescope gives us our first clues. At roughly 15 micrometers, S1 radiated heat consistent with a temperature near 220 to 250 Kelvin. That's around -50 degrees Celsius. Colder than Antarctica in winter, but warmer than Saturn's cloud tops. This is not a scorched hot Jupiter hugging its star. It is not a glowing newborn planet radiating leftover formation heat. It appears to be something quieter, older, cooler. A mature gas giant orbiting at a distance comparable to Mars in our own solar system. Its estimated mass falls somewhere near Saturn's, perhaps between 80 and 150 times the mass of Earth. Large enough to gather a thick hydrogen-helium envelope, not massive enough to ignite fusion like a star. A true planet, if confirmed. And its location is what makes it extraordinary. Alpha Centauri A is slightly brighter than our Sun. That shifts its habitable zone outward. The region where a rocky planet could sustain liquid water lies farther from the star than Earth's orbit from ours. S1's projected orbit, swinging between roughly 1 and 2 astronomical units, places it near or within that temperate band. Of course, S1 itself would not be habitable. Gas giants have no solid surface. Beneath their cloud tops, pressure increases relentlessly. What looks like ground from space is merely the upper layer of atmosphere. Descend far enough, and gases compress into exotic states of matter. There are no oceans, no continents, no place to stand. But giant planets rarely travel alone. Jupiter has more than 90 moons. Saturn has even more. Some are small and irregular. Others are worlds in their own right. Titan has a thick atmosphere and liquid lakes, though of methane, not water. Europa and Enceladus hide global oceans beneath icy crusts. These moons are not barren rocks, they are complex, dynamic environments. Now imagine such moons orbiting S1, warmed not only by internal tidal heating, but also by the steady light of a sun-like star. A large moon orbiting within Alpha Centauri's habitable zone could receive enough stellar energy to maintain surface liquid water if its atmosphere were thick enough. Instead of a frozen ocean trapped beneath the ice, water might flow openly across its surface. Clouds might form, rain might fall. 2 suns would hang in its sky. Alpha Centauri A, bright and golden, and farther away, Alpha Centauri B, smaller but still visible, casting faint secondary shadows over decades as the binary orbit slowly shifts. This is no longer abstract speculation. It is a physically plausible scenario. If S1 exists, the planet's eccentric orbit adds another layer of complexity. With an estimated eccentricity near 0.4, its distance from the star would vary dramatically over each orbital period. At closest approach, S1 would receive substantially more radiation than at its farthest point. That variation could drive seasonal extremes, not just on the planet itself, but on any moons orbiting it. Climate patterns might shift on multi-year cycles. Ice caps might expand and retreat. Atmospheric chemistry could oscillate with orbital rhythm. We have never directly observed such a system before. All previously imaged exoplanets have been young and far from their stars. They glow brightly but tell us little about mature, sun-like planetary environments. S1, if confirmed, would be the first directly imaged example of a billion-year-old gas giant orbiting within the temperate zone of a star nearly identical to our own. It would be, in effect, a mirror held up to our solar system's outer regions, placed just beyond our cosmic doorstep. There's another implication, quieter, but just as profound. For years, some theoretical models suggested that binary star systems like Alpha Centauri might struggle to form stable planets in their inner regions. The gravitational pull of a nearby stellar companion can stir protoplanetary disks, disrupting the gentle accumulation of material needed to build worlds. Yet, if S1 exists exactly where models predicted marginal stability, then those models were incomplete. Planets may be more resilient than we assumed. Binary systems, once thought hostile, may host worlds in abundance, and binary stars are common. Roughly half of sun-like stars in our galaxy exist in multiple star systems. If planets can form and survive in environments like Alpha Centauri, then the number of potential planetary systems in the Milky Way expands dramatically. That shifts the cosmic perspective. We already know planets are common. Missions like Kepler showed that most stars likely host at least one. But finding a planet around the closest sun-like star changes the conversation from statistics to intimacy. It makes the idea tangible. Alpha Centauri is not an anonymous entry in a catalog. It is a familiar star in our sky. It has guided navigators. It has inspired stories. It is the most realistic destination for interstellar travel within the foreseeable future. And now it may host a gas giant in its temperate zone. That matters because proximity changes everything. At 4 light-years, Alpha Centauri is close enough that future generations could, in principle, send probes there within decades. Projects like laser-driven light sails aim to reach relativistic speeds fast enough to cross the distance in about 20 years. If S1 exists, those missions would have a concrete target, a specific orbit, a real world to study up close. Even without interstellar travel, proximity enhances observation. A planet at Alpha Centauri appears larger in our sky than planets around stars 10 times farther away. Its light is stronger, its orbit easier to track. Future telescopes, massive ground-based observatories currently under construction, will surpass even Webb's capabilities. They may measure S1's atmospheric composition, search for methane or water vapor signatures, perhaps even detect hints of weather patterns. And if S1 has large moons, advanced instruments might one day infer their presence through subtle gravitational effects or brightness variations. All of this rests on a single unresolved question: is S1 real? If it is, then the universe has placed a Saturn-like giant in the most intriguing possible location around the star next door, within reach of both imagination and eventual exploration. If it is not, then the mystery itself teaches us something about the limits of our instruments and the subtleties of light. But here is what makes this moment extraordinary. For the first time in history, humanity has reached the sensitivity required to even ask this question about Alpha Centauri. For centuries, that star was just a point of light. Then it became a sun-like twin. Now it is a system we can probe for individual worlds. Whether S1 proves to be a planet or a phantom, the threshold has been crossed. We're no longer guessing about our nearest stellar neighbor. We're investigating it. And somewhere in that investigation, hidden in glare, emerging in infrared warmth, may lie the first confirmed world beyond our solar system that is close enough to one day feel less like a distant star and more like a destination. In science, a mystery does not linger forever. It narrows. After the disappearance of S1 in early 2025, astronomers were left with 2 broad possibilities: either the August 2024 detection was an extraordinarily rare illusion, or the planet had simply moved to a place where current technology could not see it. To decide between those options, they turned to prediction. Gravity is not mysterious. If S1 is real, it must obey the same laws that guide Earth around the Sun and Jupiter around its orbit. Its path cannot be random. It must trace a repeatable curve through space. And if that curve is mapped well enough, it tells us when the planet should become visible again. Orbital simulations converged on a crucial period, mid to late 2026. In many stable configurations, S1 would swing outward once more, returning toward a pastron, the farthest point in its elliptical orbit from Alpha Centauri A. At that distance, the planet would step out of the most intense glare, entering the narrow window where the coronagraph aboard the James Webb Space Telescope achieves peak sensitivity. In other words, the universe has set a date. If S1 exists, it should reappear. That prediction transforms the mystery into something testable. Not philosophical, not speculative, measurable. If Webb observes Alpha Centauri during that window and finds S1 near the predicted position, the case becomes overwhelming. 3 independent detections, 2019 from the ground, 2024 from space, and 2026 from Webb again, would outline a coherent orbit. Random noise cannot trace a gravitational ellipse across years. Background galaxies do not follow Kepler's laws around nearby stars. But if nothing appears in 2026, if the field remains empty despite favorable geometry, then the scales tip in the opposite direction. The August detection would retreat into the category of rare instrumental anomaly, a statistical ghost that briefly imitated a world. Either way, something profound will be learned. If confirmed, S1 becomes more than a data point. It becomes the closest directly imaged exoplanet in history. A mature, temperate zone gas giant orbiting a star nearly identical to our own, a system close enough that future telescopes and perhaps one-day spacecraft could study it in detail. And if refuted, the lesson is equally important. It sharpens the boundary between signal and illusion. It refines the techniques required to image worlds hidden in stellar glare. It strengthens future searches around other nearby stars. Because Alpha Centauri is only the beginning. The methods developed for this observation, blind offset pointing, extreme contrast subtraction, refined noise modeling, can be applied elsewhere. Other bright nearby stars, once considered too difficult, may now fall within reach. Each attempt pushes the frontier a little closer. There is also a deeper shift happening here. For most of human history, the stars were unreachable lights. Then they became suns. Then we learned they host planets. Now we're beginning to resolve individual worlds around the nearest of them. Not through inference alone, but through direct imaging. That progression changes perspective. Alpha Centauri is no longer just a bright dot in the southern sky. It is a system with structure, with orbital motion, with potential geography. It may host a gas giant tracing a stretched path every few years. It may host moons warmed by sunlight from two stars. Or it may surprise us again in ways we've not yet imagined. What Webb did was not simply detect a faint point of infrared light. It demonstrated that our nearest stellar neighbor is accessible to investigation at a level once thought impossible. The glare is no longer impenetrable. The firefly can be seen beside the searchlight. And so the story now pauses, not at an ending, but at an interval between disappearance and return, between detection and confirmation, somewhere 4 light-years away. If S1 is real, it continues its orbit without drama. It does not know it has been named. It does not know it has sparked debate across a small blue planet. It simply follows gravity as it always has. The next time Webb looks, the answer will not be ambiguous. Either a faint point of warmth will re-emerge at the predicted location, tracing the arc of an unseen world, or the darkness will remain. In that moment, decades of wondering about Alpha Centauri will crystallize into clarity. Because the universe does not hide forever. It waits for us to look at the right time, from the right angle, with the right tools. And now, for the first time, we have all three. The final answer, the truth of Alpha Centauri's great secret, will be known in 2026.